Hi, welcome back to General Chemistry 1. I'm Dr. Fang Xu. Now we are moving on to Chapter 9, which discusses all types of chemical bonds and their energy. So let's start to talk about the bonding types and electronegativity. In the General Chemistry 1 course, we say there are three ways of bonding, or three types of bonding. So it can be the ionic bonding, a chemical bond formed by electron transfer. For example, the sodium loses electrons, chlorine gain electron, it can form a sodium chloride, an ionic compound with the ionic bond. A bond can also be formed by covalent bonding, which is sharing electrons. With two chlorines or chlorine and bromine, they share electrons to form this chlorine monobromide compound. Also, a chemical bond can form by electron pooling, and it forms a metallic bonding. The metallic bonding only exists when there is a bulk of metals. Each of the metal atoms contribute electrons to the whole electron pool, and then it has a special type of bonding called metallic bonding. So when we talk about these three types of bonding, and we ask you to identify each bonding, besides the electron transfer, electron sharing, and electron pooling, we can also do a trick and determine the category of the two bonding atoms. If the bonding atom is a metal plus non-metal, then this type of bonding is ionic bonding. And there's one special case here. If we have polyatomic ion, then the polyatomic ion formed with other atoms or other groups, that bond is also ionic bonding. If we have two nonmetals, or nonmetal plus nonmetal, they can be the same or they can be different. But as long as there are two nonmetals, usually they form the covalent bonding. Okay, finally, if we have a bulk of pure metal, then it's metallic bonding. Let's take a look at a few questions. Identify bond types. What types of bonding can be found in the following species? First, calcium oxide. Calcium is metal, oxide is non-metal. Metal plus non-metal atoms, it's ionic bonding. Chlorine. Chlorine, there are two chlorine atoms here. Both of them are non-metal, so it's covalent bonding. And also there's no polyatomic ion, so it's covalent bonding. Carbon tetrachloride. All atoms here are non-metal, so it's only covalent bonding. And of course, there is no polyatomic ion. Cupric sulfate. For cupric sulfate, we have polyatomic ion and we have a metal ion, right? So iron, it's ionic bonding between copper 2+ and sulfate. However, within sulfate, we have sulfur and oxygen. Okay, so this actually are covalent bonding between sulfur and oxygens. So for cupric sulfate, we have both ionic bonding and covalent bonding. Sulfuric acid. For sulfuric acid, because we have, again, the polyatomic ion, although all of them are nonmetals, it still have ionic bonding between sulfate polyatomic ion with hydrogen. And also within sulfate itself, it's covalent bonding. So again, here we have a mixture of ionic and covalent bonding. So besides telling or identify a bond type from whether we have non-metal, metal, and polyatomic ions, there is a more accurate way for us to determine the bond type. And then we need to learn the concept about electronegativity. So electronegativity is the relative ability of a bonded atom to attract shared electrons. Okay, it's kind of similar to the electron affinity discussed in our last chapter, but it's slightly different, is for bonded atoms. So an atom with large electrical activity tend to form an anion. An atom with small electron activity tend to form a cation. As you can see in this figure 9.21, all the nonmetals, they have large electron activity, they tend to form anion. And for all the active metals, they have small electron activity and they tend to form a cation. So you also are expected to know the electron activity trend for main group elements. In general, the electron activity is inversely related to atomic size. So which means the bigger the size, the smaller the electron activity. So that means down to a main group, the electron activity decreases as we're moving from first row to the 7th row. And across the row of main group, the electron activity will increase as the size of atom decreases. And nonmetals are more electronactive than metals. Okay, just remember these general trends. And then after we know the value of electronactivity of each atom, how are we going to determine the bonding type based on the electronactivity? So that is related to the difference of the electronactivity between two atoms. So in this table, we give all the values of electronactivity of all atoms in the periodic table. The electronactivity difference, delta En, is the difference between the electronactivity of the two bonded atoms. So for example, if we want to calculate the electronactivity difference between lithium chloride, lithium has an electronactivity of 1.0. Chloride has an electronactivity of 3.0. So electronactivity difference between these two are 3.0 minus 1.0, that equals to 2.0. The same thing is, hydrogen chloride. We can find the values of electronactivity of hydrogen and chlorine in this table, and then subtract them to get the electronactivity difference, which is 0.9. The same thing as the chlorine, it's 0 because the chlorine gas is made up by exactly the same chlorine atom. So they have the same electronactivity, the difference are 0. Okay, so you can see from bottom to top, the electronactivity difference increases, right? And also if we have the chlorine, hydrogen chloride and lithium chloride, the ionic character increasing. We have a pure covalent compound to, a covalent compound by different atoms and to an ionic compound. So the ionic character increases. So that gives us an idea that the electronactivity difference can be related to bond types. So basically, we need to find the electronactivity difference of the two bonded atoms and then put that in this range. If it's 0.0, the electronactivity difference is 0, then it's, they call it non-polar covalent. It's a covalent bond. We'll talk about this polarity in our next video. Okay, we can ignore it for now. So if it's 0, then it's a covalent bond. And if it's larger than 1.7, then it's an ionic bond. If it's smaller than 1.7, it's a covalent bond. So you can see from this diagram, on the Y, it's a percent ionic character, and on the X is the difference of electronactivity. We put different compounds in this diagram, and you can see after electronactivity is larger than 1.7, we think it's more ionic, and we treat that as an ionic compound. But you can see neither of this ionic compound has 100% ionic character, which means when we have this electron transfer between the two atoms to form an ionic compound, it will never be like complete 100% transfer. It probably is like 90% transfer and with some features of electron sharing. So Just keep that in mind. No chemical bonds has a 100% ionic character, and we are based on the difference of electronegativity to determine accurately whether a chemical bond is ionic or covalent. All right, this is the end of this video, and I'll see you next time.